newly released image of 3I Atlas confirms it's not a comet, stunning researchers worldwide.
For centuries, the skies have followed predictable patterns, planets and asteroids moving in quiet clockwork. But now, 3I/ATLAS has shattered that order. Astronomers have confirmed it unleashed a massive surge of asteroids, sending rocks hurtling toward the inner solar system in numbers never seen before. Could this be the first ripple of a larger cosmic event, or the opening act of something far more dangerous? Stay with us, because what 3I/ATLAS has set in motion may change everything you thought you knew about the safety of our planet. The September 18th close call. Inside mission control centers across the world, a single designation flashes across screens: 2025 FA22. To the untrained eye, it looks like just another alphanumeric tag, but to astronomers it represents one of the most consequential near misses Earth has faced in recent memory. Calculated to pass at only 2.2 lunar distances, just over 500,000 miles, the object is close enough to trigger planetary defense protocols. This is not an abstract simulation. It is real-time, with countdown clocks now measured in days. FA22 is massive by asteroid standards, spanning nearly 170 meters across, comparable to a skyscraper laid on its side. A body of such size has the potential to release more kinetic energy than any nuclear arsenal on Earth. Moving at more than 25,000 miles per hour, it would strike with a force so immense that entire cities, perhaps even entire regions, could be erased in a single instant. Historical analogies are sobering. The Tunguska explosion of 1908 flattened 800 square miles of Siberian forest, yet the culprit was likely less than a third of FA22's diameter. The Arizona Barringer crater was excavated by an impactor less than half this size. FA22 represents a different league of threat. Even though predictions confirm that Earth will be spared direct impact, scientists emphasize that the story does not end there. Passing objects this large exert measurable gravitational effects. As FA22 swings by, it will tug imperceptibly on our planet, satellites, and even smaller space debris in orbit. These subtle nudges can cascade, altering trajectories in ways that take months to reveal themselves. The risk is not simply a strike, it is the chain reaction of orbital reshuffling that may follow. Inside NASA's Planetary Defense Coordination Office, analysts prepare radar arrays and optical telescopes to seize the opportunity. FA22's flyby provides a rare chance to map the object in extraordinary detail. High-frequency radar pulses will sketch a three-dimensional model of its surface, capturing ridges, craters, and perhaps signs of ancient fractures. By analyzing how radar beams scatter back, researchers will determine whether FA22 is solid iron or a fragile rubble pile barely held together by gravity. The distinction is crucial. A monolithic block would strike with devastating concentration, while a loose aggregate might disintegrate in the atmosphere, dispersing its energy differently. The asteroid also brings into focus the limitations of our defenses. Until recently, Earth's most ambitious protective test was NASA's DART mission, which nudged a small asteroid's orbit in 2022. That experiment proved humanity can shift a target when given years of preparation. FA22, however, is already here, bearing down at speeds far beyond the capacity of current rockets to intercept. The contrast highlights how fragile our security remains when faced with late-detected objects on steep, high-velocity paths. Adding to the unease is the discovery of FA22's unusual orbital history. Backtracking simulations suggest that only months ago, the asteroid was far outside the comfortable zone of near-Earth monitoring. Its sudden inward migration has left dynamicists puzzled. Did it drift gradually under the Yarkovsky effect, a thermal push caused by uneven heating? Or was it jolted suddenly by something else, perhaps a gravitational perturbation deeper in the solar system? The speed and angle of its approach lean toward disruption rather than slow evolution. Beyond the technical analysis lies the human dimension. amateur astronomers scattered across rooftops and rural observatories have joined in, uploading their own time-stamped images. For many, this is the first time their data has become part of an international effort to track a potential hazard. Social media threads overflow with nightly updates, blending excitement with dread. It feels like watching a bullet graze past your skin, one observer from Arizona typed after logging positional data from his backyard telescope. The passage of FA22 on September 18th will not destroy cities or alter climate. Yet the spectacle marks a threshold moment. Humanity is staring at a cosmic giant moving close enough to remind us of vulnerabilities long ignored. What makes it all the more unsettling is the emerging realization that FA22 may not be traveling alone. If this skyscraper-sized rock is only the first arrival, what else might be following in its shadow? Could Earth be staring down the opening act of something far larger? Stay with us to uncover the details. The birth of the asteroid wave. Long before dawn on September 16th, astronomers monitoring sky surveys noticed something unsettling. It was not just one asteroid streaking by, but several, all arriving in quick succession. Computer dashboards lit up with multiple near-Earth approach alerts, their timestamps clustered within hours of one another. What had been described as a singular flyby now resembled a traffic jam in space. The term quickly spread through labs and newsrooms, the asteroid wave. Each object had its own designation, small alphanumeric tags that barely hinted at the scale of what was happening, while none matched the imposing size of 2025 FA22, several measured over 100 feet across, large enough to cause regional devastation if they entered the atmosphere. More curious was the timing. Ordinarily, near-Earth asteroids arrive sporadically, separated by weeks or months. Here, the arrivals were tightly bunched, like a formation of aircraft appearing in sequence. As tracking data accumulated, patterns began to emerge. Many of the objects seemed to share similar orbital inclinations, tilting toward Earth from an unusual angle relative to the plane of the solar system. The clustering was too sharp to be chance. Something had disturbed their orbits recently, nudging them toward Earth's neighborhood almost simultaneously. At the European Southern Observatory, specialists ran orbital backward propagation models, retracing the paths of the intruding asteroids. Instead of dispersing chaotically, their trajectories seemed to converge in the outer reaches of the solar system. The implication was stark. These rocks had not arrived independently. They were part of a disturbed stream, set loose in the same cosmic event. Theories raced across conference calls. Some pointed to a gravitational resonance with Jupiter, a subtle dance of orbital mechanics that can destabilize small bodies over decades. Others suggested a recent collision between two larger asteroids, scattering fragments inward. But the most provocative explanation came from those who suspected an outside influence, something massive and fast-moving that had sliced through the distant Oort cloud or Kuiper belt, shaking loose a chain of debris. For planetary defense officials, the distinction hardly mattered in the immediate sense. The reality was that Earth now faced multiple close approaches in rapid succession, increasing the statistical likelihood of an unexpected strike. Unlike FA22, which was large enough to be tracked well in advance, the smaller members of the wave often appeared with little notice, detected only days before their pass. The margin for response was razor-thin. Beyond the technical community, the asteroid wave sparked a mix of awe and alarm. Public fascination grew as nightly sky charts circulated online, marking the approach of each visitor. Headlines carried phrases like cosmic storm and celestial barrage, framing the events less as isolated encounters and more as symptoms of a larger hidden process unfolding beyond sight. Amid the buzz, one fact became undeniable. The wave carried a fingerprint of orchestration, as though invisible hands had jostled the pieces into motion at once. The timing, the clustering, the angles, They all pointed back to a single question that observers whispered in late-night data sessions. What or who had started this? If FA-22 was the warning shot, then the asteroid wave was the full signal flare. But where exactly did that flare originate? And what does it reveal about the intruder now suspected of pulling the strings? Come with us to find out more. The interstellar intruder, 3I/ATLAS. On the morning of July 1st, 2025, a faint flicker appeared on the digital monitor of the Atlas Survey Telescope in Chile. To most, it would have seemed like a meaningless blip of static, a stray point lost in the flood of nightly sky data. Yet within hours, that anomaly was confirmed as something extraordinary, an object not bound to our sun, but cutting through the solar system on a hyperbolic path. It was quickly catalogued as 3I/ATLAS, marking only the third confirmed interstellar visitor humanity had ever recorded. Unlike the familiar comets and asteroids born from our local cosmic neighborhood, ATLAS did not belong here. Its velocity, angle of entry, and trajectory all betrayed a deep space origin, launched from a star system humanity may never know. From the outset, astronomers recognized that this was not a simple icy wanderer. Its brightness fluctuated strangely, its light curve irregular, hinting at something beyond the typical behavior of frozen debris. What made Atlas so unsettling was not only its origin, but also its peculiar activity. Spectroscopic campaigns launched by observatories across the globe revealed periodic surges in emission lines, as if the object were pulsing at regular intervals. Comets normally vent gas in chaotic bursts driven by heat and subsurface fractures. Atlas, however, released material in precise, clock-like rhythms. This mechanical consistency unsettled even seasoned scientists, raising questions that veered into territory usually reserved for science fiction. Even more striking was the composition. Alongside expected volatiles like carbon monoxide, telescopes recorded a narrow reflective spike in the near-infrared spectrum. The signal was sharper than any known mineral signature associated with natural cometary dust. To some, it resembled polished metal, a surface too uniform to be explained by random fragments of rock or ice. The possibility that Atlas carried elements of artificial origin, though unproven, was serious enough to appear in internal memos circulated between research institutions. Orbital analysts faced their own challenge. Standard gravitational models failed to capture ATLAS's trajectory accurately. Each new dataset forced recalibration, as if unseen forces were subtly adjusting its path. Non-gravitational accelerations are known in comet science, usually explained by uneven jets of gas acting like thrusters. But Atlas's thrusts occurred with unnerving precision, aligning perfectly with its emission pulses. What appeared as cometary venting in the data also behaved like controlled propulsion. As calculations converged, one truth became unavoidable. Atlas's approach corridor brought it dangerously close to Mars, with some simulations threading its path within 50,000 kilometers of the planet's surface. At speeds near 90 kilometers per second, even a near miss could have catastrophic side effects, disturbing moons, satellites, and orbital trajectories in ways that planetary defense models had never prepared for. International agencies treated the object with unprecedented seriousness. Harvard researchers forwarded early alerts to NASA's Minor Planet Center, while European and Asian observatories poured resources into constant monitoring. The interstellar status of ATLAS gave it special weight. Unlike routine comets, this one could not be expected to return. It was a once-only event, passing through our cosmic backyard and leaving consequences that might echo for decades. Behind closed doors, debates grew sharper. Was Atlas simply an unusually active interstellar comet, driven by exotic chemistry unknown in local bodies? Or was it something qualitatively different, an object not entirely natural in origin? For planetary defense planners, The answer was less important than the practical implication. Its unpredictable bursts made trajectory forecasting nearly impossible. The asteroid wave that followed in the weeks after its arrival seemed to strengthen suspicions. When backward propagation simulations were run on the smaller intruding asteroids, many paths traced back toward the region disturbed by ATLAS's entrance into the solar system. The idea that this single visitor had acted like a gravitational hammer, dislodging countless smaller bodies from the Oort cloud and hurling them sunward, became difficult to dismiss. Yet questions remain unanswered. If Atlas's pulses are natural, why do they mimic engineered systems? If its reflectance spike is geological, why has no other comet produced a similar signature? And most unsettling of all, if its gravitational influence can scatter asteroid fields, what does that mean for the stability of Earth's own orbital environment? Could it be that 3I/ATLAS is not just passing through, but leaving a trail of disruption that humanity has only begun to measure? Stay here as we reveal everything. Swan 25b, the freshborn comet. Astronomers expect comets to announce themselves long before they reach the inner solar system. Usually, a frozen nucleus begins shedding gas as sunlight warms it, forming a diffuse tail visible for months, sometimes years. That is the ordinary script. But in early July 2025, a new entry appeared in sky surveys with no warning at all. It carried the provisional designation Swan 25b, and its behavior from the outset defied every model. Instead of creeping into visibility as a faint smudge, Swan 25b burst into existence already glowing with remarkable brightness. Observers using the SWAN instrument aboard the SOHO spacecraft, an instrument meant to track solar wind, not comets, were the first to register the anomaly. In a matter of days, its apparent magnitude surged, outpacing predictions by orders of magnitude. To planetary scientists, the rate of brightening suggested something extraordinary. This was not an old, weathered comet returning from countless past orbits. It was fresh, likely on its maiden voyage into the inner solar system. The mystery deepened as ground-based observatories brought more data. Comets typically display gradual acceleration as their jets fire unevenly, causing slight wobbles in trajectory. Swan 25b's motion, however, was remarkably steady, almost as if its outgassing was uniformly distributed across its surface. That uniformity raised unsettling questions. Was this a fragment knocked loose by a violent gravitational encounter? Or was some hidden mechanism at work beneath its crust, regulating its eruptions with unusual precision? Spectroscopic analysis revealed further surprises. Alongside the expected water vapor and carbon-based volatiles, Swan 25be displayed faint emissions in unusual wavelengths. One line in particular suggested the presence of molecular compounds rarely observed in comets at such early stages of activity. These compounds hinted at a pristine origin, material that had likely remained undisturbed since the birth of its parent star system billions of years ago. The implication was sobering. Swan 25b might carry chemical fingerprints not of our Sun's nursery, but of a distant stellar environment entirely. Its projected path added to the unease. Orbital simulations predicted that Swan 25b would sweep close to Earth in October, only weeks after Asteroid 2025 FA22's near miss. While not a direct impact threat, its proximity was close enough to warrant intensive monitoring. Scientists recognized the timing as more than coincidence. The odds of an interstellar object like 3I/ATLAS disturbing both an asteroid and a comet within such a narrow time frame seemed improbable, yet the data pointed that way. Swan 25b could be another shard of fallout from the same cosmic disruption. Public reaction grew quickly once images began circulating. Amateur astronomers marveled at its rapid brightening, posting photographs of a comet already boasting a visible tail despite its distance from the Sun. News outlets branded it the comet that came out of nowhere, drawing comparisons to historical great comets that dominated the sky. For many, its sudden appearance felt like a celestial omen arriving on the heels of the asteroid wave. Inside research institutions, however, the atmosphere was anything but romantic. Emergency workshops convened to review SWAN 25B's volatile behavior. Could its interior pressure build to the point of fragmentation? If it were indeed a fresh body on its first pass, its nucleus might be riddled with weaknesses. A sudden breakup could scatter dozens of smaller objects across Earth's orbital path, multiplying risks in unpredictable ways. The debate soon shifted toward cause and connection. Did 3 I/ATLAS's gravity deliver SWAN 25B into our skies? Was its first awakening from the deep triggered by that same interstellar visitor whose pulses had already defied explanation? For some, the comet was not just another icy traveler, but a breadcrumb, evidence that ATLAS had unsettled far more than initially suspected. And if SWAN 25B is only the first of such disturbed comets to appear, what new arrivals might follow in its wake? Come along as we uncover the hidden story. Visitors from the Void. For most of recorded history, humanity assumed the night sky was a closed system. Every comet, asteroid, and meteor streaking overhead belonged to the same cosmic family that formed alongside our Sun 4.5 billion years ago. That illusion shattered in October 2017 when telescopes caught sight of Oumuamua, an elongated object hurtling through the solar system on a path no gravity well could reclaim. It was the first undeniable interstellar visitor, an emissary from a star system far beyond our own. 2 years later, another alien wanderer appeared, Comet Borisov, an icy body with a glowing coma, behaving more like the comets we knew, yet still bearing the unmistakable velocity of an outsider. The scientific world suddenly found itself confronting a truth once reserved for speculation. Our solar system is not isolated. It is porous, a crossroads where material from distant stars can and does arrive uninvited. Now comes 3 I/ATLAS, the third confirmed interstellar object and by far the most disruptive. Unlike its predecessors, ATLAS has not simply passed through as a curiosity. It has left trails of consequence, reshaping the dynamics of asteroids and comets in our neighborhood, and possibly igniting the very surge of celestial traffic Earth now faces. The difference between passive observation and active disruption has forced astronomers into new territory. For the first time, they must grapple with the possibility that interstellar debris can alter the stability of our planetary environment. What makes these visitors so vital to study is not only their trajectories, but their compositions. Every fragment carries the geochemical story of its birthplace. Oumuamua's surface appeared strangely metallic and inert, lacking the vaporous tail expected of comets. Borisov, by contrast, displayed gas signatures consistent with typical icy bodies but in unusual proportions, hinting at chemistry shaped by a different star's radiation. If Atlas follows this pattern, it may reveal an entirely new set of compounds, unrecorded in our own system. Such discoveries are not just scientific trivia, they are windows into how planetary systems form across the galaxy. But the case of ATLAS goes further. Its anomalous pulses, its metallic glints, and its uncanny gravitational influence set it apart from earlier interstellar guests. The data suggest more than passive drift. Something about Atlas behaves as if it carries internal mechanisms or structures not explained by natural models. For some in the scientific community, this raises an uncomfortable but unavoidable hypothesis. What if interstellar objects occasionally carry remnants of technology? Ancient and inert perhaps, but technology nonetheless. The term technosignature, once confined to the search for distant radio beacons, is now whispered in connection with ATLAS's unexplained signals, International research coalitions are beginning to treat these interstellar encounters as more than isolated anomalies. Proposals circulate for dedicated telescopes positioned beyond Earth's atmosphere, designed solely to capture the next visitor with greater clarity. There is recognition that each passing body may represent a once-in-a-lifetime chance to sample the chemistry and perhaps even the artifacts of other star systems. Unlike stars themselves, which shine across light years, these objects come to us physically, carrying unaltered matter from alien nurseries. They are not distant observations, they are tangible deliveries. The public fascination mirrors the scientific urgency. News networks frame Atlas as the object from another world, while social platforms pulse with speculation ranging from alien probes to galactic messengers. While much of this is exaggeration, it underscores a deeper truth. Humanity has never before been so directly confronted with physical material from beyond its own stellar cradle. Atlas is not just another rock in the sky, it is evidence that we live in an open system, part of a galactic web where borders do not exist. And yet, with every revelation, one question grows sharper. If these visitors can reshape asteroid belts and send comets surging toward Earth, then what other forces might follow them? Are they scouts of something greater or simply random fragments caught in the tides of galactic drift? Let us tell you. The real wake-up call. Inside NASA's secure briefing rooms, the tone has shifted from curiosity to contingency. No one is debating whether Earth will be struck on September 18th. Calculations show a clean miss, but the broader implications are far more sobering. For the first time, humanity is staring at a chain of events triggered by an interstellar visitor, a cascade that has disrupted asteroids, awakened comets, and exposed weaknesses in planetary defense strategy. The truth is stark. Our current detection systems, while powerful, remain limited. Ground-based telescopes are blind to objects approaching from the direction of the Sun. Radar coverage only extends so far. For every one near-Earth asteroid catalogued, thousands remain unseen, drifting silently in space. The asteroid wave of 2025 demonstrates how quickly multiple threats can converge, leaving only days of warning rather than years. Beyond hardware, the legal and political frameworks are equally unprepared. The Outer Space Treaty of 1967 never contemplated planetary defense, let alone responsibility for protecting assets on other worlds. If Swan 25b were to fragment and scatter debris across Earth's orbit, who would coordinate the response? Who decides which satellites to safeguard, which missions to suspend, and how risks are shared across nations? At present, there is no unified doctrine. Each agency operates in isolation, improvising as events unfold. Yet, there are glimmers of progress. The success of NASA's DART mission in altering an asteroid's orbit has proven that intervention is possible. New proposals envision constellations of dedicated survey telescopes spread beyond Earth's orbit to monitor the skies with unprecedented coverage. Private aerospace firms are also entering the discussion, exploring rapid launch interceptors capable of responding to short-notice threats. What was once science fiction is now being modeled in draft plans. But the ultimate lesson of Atlas and the asteroid wave is not simply about technology. It is about perspective. Humanity has long seen itself as insulated, orbiting a stable sun under predictable celestial mechanics. The last few months have shattered that illusion. The cosmos is dynamic, volatile, and sometimes dangerous, and we are participants in a system far larger than we ever imagined. What do you think is the real cause of this asteroid surge? The strange gravitational pull of 3I/ATLAS? The mysterious energy pulses it released? Or an even deeper cosmic chain reaction we have yet to uncover? Share your thoughts in the comments.